Hello and welcome to another online lecture for General Physics 2. This one deals with the concept of series and parallel circuits, and what we mean in this is that we're expanding on what we did before, where we had the simplest circuit imaginable, some power supply like a battery, connected to one thing that resisted the flow of electricity through that circuit, like one light bulb. Well, now we're dealing with the idea of what happens when you put two or more resistors, could be light bulbs, could be carbon resistors, could be something else, in series with one another and in parallel with one another. And in this discussion we'll define what we mean by those terms. So a series circuit is a circuit where, and this one just shows two resistors, but you hook the resistors so that there is still one path for the current to travel in this circuit. So the resistors are hooked end to end to each other and then to the battery. And because there's only one path in this circuit, when we measure the amount of electric current that's after the battery or before the first resistor or in between the two resistors or after the second resistor or before it enters the battery, we find that there's the same amount of current flowing through each of these devices. This is confusing to some people because, again, you expect something to have diminished after the charge has flowed through each resistor. And in fact, something has diminished, but it's not current. Current, you'll recall, is charge per time. So all we're saying by saying the current is the same everywhere in this circuit is that there are the same number of charges passing each observation point per time in there. In other words, we're not creating charge, we're not destroying charge, we're not building charge up within the resistors, we're just pushing charge around this loop. The potential difference across the power supply, though, if we measure the potential difference across the power supply, that's the voltage of the battery, it gets divided among the resistors. So the potential difference across resistor 1 plus the potential difference across resistor 2 is equal to the potential difference across the battery. The way I think about this is when you pump charges through the battery, it increases the energy of those charges by a certain amount. So if I have a 9-volt battery, each coulomb of charge that I pump through the battery gets an increase of 9 joules of electric potential energy by the action of pumping it through the battery. And then as those charges pass through the resistors, they transfer some of that energy to the resistor, which converts it into heat. And so the gain that I experience going across the battery must be the same as the drops or the decreases in energy that I experience passing through the network of resistors. So we're going to use these two ideas in Ohm's law to piece together ideas about equivalent resistance in a series circuit. So the electric potential across the battery, here I'm using V just to match the picture, I'd prefer delta V myself, equals the potential difference across resistor 1, V1, plus the potential difference across resistor 2, which is V2. Ohm's law says electric potential difference is equal to current times resistance, so we can replace these V1 and V2 by I times R1 in the case of V1 and I times R2 in the case of V2. I didn't label I's with I1 and I2 because, again, we measure the same amount of current everywhere in a series circuit, so we can just use the generic I. That I will factor out, leaving you with I times R1 plus R2, and R1 plus R2 can be considered the equivalent resistance of the circuit, because again Ohm's law says potential difference equals current times resistance, and the equivalent resistance is therefore the sum of the resistances that we've connected in series, R1 plus R2 plus R3 plus however many of them you have in series. So if we put some specific numbers on this circuit, we have a 12-volt battery, say, a 6-ohm resistor, and a 3-ohm resistor. That would be equivalent to having a 12-volt battery connected to a single resistor, but that single resistor would have to have a resistance of 9 ohms for the circuit on the right to function the same as the circuit on the left. And this is, again, called drawing an equivalent circuit, and it's something we're going to do quite often in this section as we work to analyze what's going on in various parts of an electric circuit. So now we want to do a little bit of work. We have some numbers, so why not? Let's find the current through each resistor. what the voltage drop is across each resistor, and how much power is dissipated by each resistor in this picture. So current first. Well, I would start with the quote-unquote simpler equivalent circuit on the right, because that will have the same current flowing through it as the one on the left, since it has the same total amount of resistance. If I apply Ohm's law, potential difference equals current times resistance, or current equals potential difference divided by resistance. The battery provides 12 volts of potential difference. That will be the same as the potential difference across this 9 ohm resistor, divided by 9 ohms of resistance, and I come up with 1.33 amps, or 4/3 of an amp for you fraction fans out there. So how much current will be going through the 6 ohm resistor? Well, it's got to be the 1.33 amps. How much goes through the 3 ohm resistor? Again, it has to be the 1.33 amps, because in series circuits we observe, when we do this in the lab, that the amount of current is the same at each point around that loop. Alright, let's go to voltage drops. Well, how much is the potential difference, or the voltage drop, across each of these resistors? Well, the 6 ohm resistor has 1.33 amps of current going through it, so we can apply Ohm's law. Potential difference equals current times resistance, and you take the 1.33 amps times the 6 ohms, and you find that the potential difference is 8 volts across the 6 ohm resistor. If you do the same kind of analysis with a 3 ohm resistor, the 1.33 amps through a 3 ohm resistor will undergo a potential drop of 4 volts, and we can check ourselves if this works. The potential difference of the battery is 12 volts, the potential drop across the 6 ohm is 8 volts, and the potential drop across the 3 ohm resistor is 4 volts, so it's a gain of 12 and a total drop of 12 as well. This idea, by the way, is going to be formalized as one of 2 laws from the Kirchhoff's rules discussion that we will go into next. Alright, how much power is dissipated by each of these resistors? Well, recall from our class discussion on problem solving that electric power is electric potential difference times current, and so to figure out how much power each one's dissipating, I take the voltage that I calculated and the current that I calculated. In the case of the 6 ohm resistor, 8 volts times 1.33 amps gives me 10.6 watts. In the case of the 3 ohm resistor, 4 volts times 1.33 amps gives me 5 watts, and collectively I get about 16 watts of power that's dissipated. But I like to, again, rather than just calculating things with a formula, think about what the heck does this mean? Well, power is energy per time, so the same amount of charge is flowing through each of these resistors, but the one that's flowing through, as the charge flows through the 6 ohm resistor, it's undergoing a larger potential difference. That means more of the energy that's being carried by that charge is being transferred to the 6 ohm resistor than is being transferred to the 3 ohm resistor. And therefore the rate at which the 6 ohm resistor is dissipating energy should be higher. It's receiving more from the charges that are being pushed through it. Parallel circuits are arranged a little bit differently. Here, each resistor has what could be considered an independent connection to the battery. So the battery is connected via a wire up to this point, but then any charge that arrives at this point could pass through resistor R1 and then go back to the battery, or could pass through resistor R2 and go back to the battery. What you will not see is current coming to this point and passing through R1 and then going back through R2 in the opposite direction, because that's equivalent of things naturally rolling uphill. It would be going an increase in energy going through that resistor, which we don't observe happening if we measure these currents. So in a parallel circuit, there's the same potential difference across each of these devices, because again, whatever energy gain my charges undertake going through the battery is the same as the energy drop they experience going through either of those resistors. What splits in a parallel circuit is the current. And so when the power supply puts out a current, which we're calling I here, when it arrives at this point, some fraction of that current, I1, goes through resistor R1, and the rest of it, I2, goes through resistor R2. If you have more parallel branches, by the way, the current splits into more sub-amounts of current and goes through each of those resistors according to how resistive each path is. Okay. So if the current I splits into I1 plus I2, we can use Ohm's law to say, well, I1 is V, the potential difference across R1, divided by the resistance of R1. And V is, again, the potential difference of the battery, but that's the same as the potential difference we measure across each resistor. The current through R2 is equal to the potential difference across R2 divided by the resistance of resistor 2. The V's are the same in each thing, so those can get factored out. And so we have an expression that says I, the current coming out of the battery, is equal to V, the potential difference across the battery, times 1 over R1 plus 1 over R2. And that whole thing in parentheses can be treated as 1 over the equivalent resistance. And so 1 over the equivalent resistance is 1 over R1 plus 1 over R2, in this case when we have 2 resistors in the circuit. If we had more, you'd just keep adding terms, but you add the inverses and then take the inverse of the result to find the equivalent resistance in a parallel circuit. The math may not seem intuitive, but I encourage you to think a bit about what the concept is saying. We're adding extra resistors, but the way that we're adding those resistors means the overall resistance of the network goes down. To me, the most helpful analogy in this is to think about, checkout lines in a store or toll booths on a highway. If there is only one checkout line or toll booth open, all of the shoppers or all of the cars have to pass through that area. But if you open up another checkout register, you open up another toll booth, they are arranged in parallel to one another, so you as the shopper can decide to go to cashier 5 or cashier 8. And you can also drive through one toll booth line or the other, and that has the effect of actually decreasing the resistance of that part of the store or that part of the highway and increasing the flow of shoppers or traffic through that place as well. So this, again, can be reduced to an equivalent circuit. So if I have, and again I got some specific numbers here, if I have a 6 volt power supply hooked to an 8 ohm resistor and a 4 ohm resistor, the equivalent resistance of those resistors turns out to be 2.67 ohms and a 6 volt power supply. The little squiggle you see here on the power supply technically means that this is an AC power supply, alternating current. But we've yet to introduce what alternating current is or how to reason about that. So I'm actually going to just treat this as a direct current power supply for the analysis in this particular problem. Once again, we want to find how much current's going through each resistor, what's the voltage drop across each resistor, and how much power is dissipated by each of these resistors. Well, the equivalent resistance can be found, and it showed it on the slide, but here's the math. 1 over the equivalent resistance is equal to 1 over the resistance of resistor 1 plus 1 over the resistance of resistor 2. So that's 1 over 8 ohms plus 1 over 4 ohms. That is equal to 0.375 if you're a decimal fan. If you're not, that would be 3/8. But the equivalent resistance is the inverse of that. So you flip that over. And so that's 1 over 0.375 or 8 over 3. The equivalent resistance ends up being the 2.67 ohms that's labeled on the diagram above. And I guess one of the places I see people occasionally messing up when they're analyzing parallel circuits is they add up all of the inverses to the resistors, but then they don't invert the final result. So as you're solving parallel circuit problems, keep an eye out for that. The current through each resistor can be found by applying Ohm's law. So current equals potential difference divided by resistance. If I have a potential difference of 6 volts across each of these resistors, I take the 6 volts divided by the 8 ohms of resistance and find that 0.75 amps of current goes through the 8 ohm resistor. Do the same kind of thing for the 4 ohm resistor, and we find that there's 1.5 amps of current that goes through resistor 2. Again, conceptually you can think about this. Which of these two branches has the least resistance? Well, the R2 branch does. It has half as much resistance. It therefore gets twice as much flow of charge, or twice as much electric current. The voltage drop across each resistor, that's the easy one. We can write that down from inspection because the definition of two things in parallel are that they have the same potential difference across each other. And if you have things in parallel connected to the battery, the potential difference across each of the resistors will be equal to each other and equal to the potential difference across the battery. So it's 6 volts across all of those resistors, and in fact we've already made use of that idea to calculate the current through each resistor. The power dissipated, again, can be found by the potential difference multiplied by the current. We know both of those pieces of information now. So if we take 6 volts times 0.75 amps, we get 4.5 watts. If we take 6 volts times 1.5 amps, we get 9 watts, and a total power dissipation of 13.5 watts. Notice here, though, which resistor is dissipating the most energy, and that is the smaller resistor, the 4 ohm resistor. The way I think about it is this. The energy difference across each of those resistors in a parallel arrangement is the same. So each of the charges that enters the resistor is going to be carrying the same amount of electric potential energy, but more of those charges are going to go through the 4 ohm resistor, and it is going to end up dissipating more total energy because more charges end up flowing through that path. So here's a conceptual question. As always, I would encourage you to pause the presentation and think about an answer before you listen to my reasoning about this. But one of the circuits in this drawing has no resistors in series or in parallel with any other resistor. Which one is it? The correct answer for this is C, but let's go through one by one and show how we end up deducing that. Again, for two things to be in series, by definition, they have to have the same amount of electric current flowing through them. For two things to be in parallel, they have to have the same electric potential difference across them. And that's a trickier concept, but the more you build these circuits in lab and measure things, hopefully the more natural it comes to think about what those voltages might be. Okay, so if we go in circuit A, the current comes out of the positive end of the battery, and all that current has to go through this first resistor right here. And then it arrives at the point actually where the current's going to split and go 4 different ways, but I'm going to think about the top path because that's going to be the one that eliminates this from consideration for me. Any of the current that continues up through this resistor will have to pass through this resistor, and that means that these two top resistors are considered to be in series with one another, hence this can't meet the conditions of the question. If I look in B, I won't have that. I don't have anything in series with anything else, but because the current passes through here and then splits at this point, if I were to take my voltage probe and measure the voltage drop across this resistor right here and this resistor right here, I would find that they would match each other because each end of that network, so if I go from this end of this resistor, I can connect over here to this one, same thing over here, and because conducting wires are considered to have no resistance and therefore no potential difference across them, the potential difference across these two resistors has to match. Potential difference across these two resistors has to match. The potential difference across these two resistors has to match. So the middle one actually has 3 pairs of parallel resistors within it. C has none of the above, though, and it's because of this little middle resistor. There's no resistors in here that are connected so that the same amount of current flows through each one, and you wouldn't measure the same voltage across this resistor here as you would across this resistor here, because there is some potential difference across the resistor in the middle, meaning the electric potential value at this point in the circuit is going to be different than the electric potential value at this point in the circuit. Same logic would apply to this pair over here, so circuit C has no series or parallel connections. So one of the things we do when we analyze complicated circuits that consist of more than one resistor is we look for resistors that are either in series or in parallel to one another, and then we find the equivalent resistance to that circuit before we do further analysis. And we showed that on the slides that we defined series and parallel circuits on. Well, here's a more complicated circuit. We threw 4 resistors in there, and it turns out that many circuits, both the made-up ones of physics problem world and the real ones that are in your electronic devices, consists of many circuit elements that are in parallel to one another and other circuit elements that are in series to one another. And we can use this idea about series and parallel circuits to figure out what the equivalent resistance is in a given circuit. And often, once we have the equivalent resistance in the circuit, we then work backwards through our analysis to figure out what the various quantities are at various places in the circuit. For example, how much current goes through this branch, or what is the voltage across that resistor. So here I have 4 resistors hooked to a 24-volt power supply, and I look and I say, in this, do I see any that are in series or in parallel with one another? Well, the 110 is not in series or parallel with anything, because it won't have the same voltage measured across it as anything else. And whatever current goes through the 110 is the total current that went through the battery before it arrives here at point A and splits. But if I look all the way over here, I do notice that these 2 resistors would be considered to be in series with one another, because the same amount of current that passes through the 220 ohm resistor has to also pass through the 250 ohm resistor. The combined resistance in that path is the combined resistance of those resistors, since we just add those values. So that is equivalent to 470 ohms of resistance. So notice I've slightly simplified the circuit by changing 2 of those resistors into a single equivalent resistor of 470 ohms. Now I look at this and I say, well, now that equivalent resistor that I just made, that 470 ohm resistor, is in parallel with a 180 ohm resistor, because again I can connect one end of one resistor to one end of the second resistor, and also similarly connect the second ends of each of those resistors without passing through any other resistive elements in the circuit. Therefore, they will have the same electric potential difference if I measure across each of those resistors. So I add those up using the inverse rule, and I haven't showed this on this slide, but I've shown similar calculations elsewhere. I would add 1 over 180 plus 1 over 470 and get a result, and then the inverse of that result is about 130 ohms of resistance. So we've now simplified from 4 total resistors down to 2 total resistors. Now that we have the 2 resistors, we say, okay, these 2 that are left are now in series with one another, because the same amount of current would have to pass through them. Series resistors add, so there must be 240 ohms of total resistance in this circuit connected to a 24-volt battery. Here I could, given a certain problem, start to work backwards, because I would say, well, Ohm's law says I've got a 24-volt power supply and 240 ohms of resistance. The current must equal the voltage divided by the resistance, so there must be 1/10 of an ampere of current flowing through this circuit. That means there's 1/10 of an ampere going through this 110 ohm resistor, which I had in my original circuit, and then I can figure out what the voltage difference is across the 110 ohm resistor. There's also that 1/10 of an amp going through this equivalent resistor, so I could figure out the electric potential difference between points A and B, and use that to figure out how much current was going in each of these branches. And so essentially when you do this analysis, you end up finding a voltage, using that to find a current, using the current to find a voltage, using that to find a current, and repeating that pattern until you know all of the information about a circuit that you want to know. We're going to do a little bit of that here, and also revisit the concept of electric power. Determine the power dissipated in the 5 ohm resistor in the circuit shown in the drawing. So right here's the 5 ohm resistor. How much electric power is being dissipated there, or converted to thermal energy from electrical energy? Well, we're going to have to do some analysis work to get there. We're going to need to know the potential difference across the 5 ohm resistor and the current going through the 5 ohm resistor. Turns out actually we can know one or the other of those, because we know the resistance and there are power equations that involve just current and resistance or just voltage and resistance. So here's our circuit. Let's start doing some analysis. If I look at this, first of all, the 2 ohm and the 1 ohm resistor are in series with one another, as are the 5 and the 1 ohm resistor. So I'm replacing those with 2 equivalent resistances. In the top branch, that's 3 ohms of resistance. In the bottom branch, that's 6 ohms of resistance. Nothing else about the circuit has changed. But now I look at this simpler circuit where I've taken 5 resistors and reduced them to 3. Now the 6 ohm resistor and the 3 ohm resistor are in parallel to one another. And because they're in parallel to one another, we can add them using the rule for adding parallel resistors. 1 over 3 plus 1 over 6 equals 1 over the equivalent resistance, and that means the equivalent resistance to that network is 2 ohms. So now I'm in a situation where I have that original 4 ohm resistor connected to an equivalent resistance of 2 ohms. Now these two are in series with one another, and that's 6 ohms of total resistance, and you have a 12 volt battery. Now we start working backwards and we apply Ohm's law and we say, okay, how much current does the battery pump out? Well, the battery will pump out current equal to the potential difference across the battery divided by the equivalent resistance of the circuit. That's 12 volts over 6 ohms, or 2 amperes of current coming out of the battery. So that 2 amperes of current is going to come out of the battery and arrive at the 4 ohm resistor. And all of that current has to go through the 4 ohm resistor before arriving at this point where it can split. So we can use that fact to figure out what the potential difference is across the 4 ohm resistor. There's 2 amps of current going through it. It has 4 ohms of resistance. That means there's an 8 volt potential difference, or an 8 volt voltage drop, as the current flows through the 4 ohm resistor. So the current goes up by a potential of 12 volts going through here, and then drops by 8 volts going through the 4 ohm resistor. Because we know that the electric potential difference across this part of the network right here must equal the same 2 amps of current going through this equivalent resistance times 2 ohms of resistance, and that's 4 volts. Again, we can check up 12 volts, down 8 volts, down 4 volts gets us back to 0. Alright, so if we know there's a 4 volt potential difference across this equivalent resistance, that's got to be the same 4 volt potential difference across this network, which we replaced with that equivalent resistor. So that means there's a 4 volt potential difference across the 3 ohm resistor. There's a 4 volt potential difference across the 6 ohm resistor. Using that fact, we can figure out how much current is going in each of those branches. So the current through the 6 ohm resistor is going to be that 4 volts of potential difference divided by 6 ohms of equivalent resistance. That's 2/3 of an amp that goes through this branch. And the top branch is going to have twice that, or 4/3 of an amp. Again, it's a potential difference of 4 volts across a resistance of 3 ohms, so we have 4/3 of an amp. Here's another good place we can check to make sure our calculations are right. We said there is 2 amps of current coming out of the battery. It's all going here and arriving at this point. And now it's splitting, and we calculated that one branch gets 2/3 of an amp, one branch gets 4/3 of an amp. If you add those together, 2/3 plus 4/3 is 6/3, which is the same as 2. And 2 amps of current is what we expect, because 2 amps of current is what we had coming out of the battery. Alright, so we now know how much current's going through this 6 ohm resistor. There's 2/3 of an amp of current going through this bottom branch. That means 2/3 of an amp go through the original 5 ohm resistor that we're asked to analyze in this problem. And that means we can calculate what the voltage drop is across the 5 ohm resistor. It's that 2/3 of an amp times 5 ohms of resistance, and that is 10/3 of volts, or 3.33 volts if you prefer. And now we can figure out how much power is dissipated by that 5 ohm resistor, because power is the electric potential difference across the resistor times the current through the resistor. That's 10/3 of a volt times 2/3 of an amp. That's 20/9 of a watt, or if you prefer, that's what, roughly 2 watts of power being dissipated by the 5 ohm resistor. Here's another practice problem. Let's determine the equivalent resistance between points A and B for the group of resistors in the drawing. Notice that this is no longer a complete circuit because we haven't connected any power supply to it. But you could connect a battery between points A and B and send an electric current through this circuit. We're just tasked with finding, if I had to replace this whole network with one resistor, what size of resistor should we use? So let's try that. All right, so I'm again on the hunt for series and parallel resistors within this that I can then sum. And if I start, I would say, well, I can start a lot of places, but there are a 4 ohm resistor here that is in series with the 6 ohm, because if there were a current going through here, the same current would have to go through the 4 as goes through the 6 ohm. The 8 and 9 ohm resistors here are in parallel with one another because they have their opposite ends connected by conducting wire, so they'll have the same potential difference across them. Let's start by actually doing both of those things simultaneously. So 4 and 6 ohms gives me 10 ohms of resistance in the rightmost branch. This middle branch can get replaced by the equivalent resistance to a 9 ohm resistor and an 8 ohm resistor in parallel with one another. So we have 1 over 9 plus 1 over 8. The common denominator there turns out to be 72, so we have 8 70-seconds plus 9 70-seconds, and so that works out to be 17 over 72. If you flip that around to find the equivalent resistance, that's 72/17 of an ohm. That is about 4.24 ohms for those of you not committed to the fraction. Okay, now if I look here, that new equivalent resistance that I found and the other equivalent resistance are now in parallel with one another because of the way they're connected. And so I can find the equivalent resistance of that together. The inverse of 72/17 of an ohm is 17 over 72, plus 1 over 10, which is the equivalent resistance, or rather the resistance of the equivalent part of that circuit. And let's see, I think the common denominator is 360 between the two of those. If you do the math, you come out with 360 121sts of an ohm, or just under 3 ohms of resistance. That part is now in series with the 3 ohm resistor, and you put those together and you add them directly. And you end up with 723 over 121 of an ohm, or again just under 6 ohms there if you're going with your decimal. And then that equivalent resistance is in parallel with the 20 ohm resistor, so we do 1 over 20 plus 121 over 723. I really committed to the fraction here. The common denominator there is 14,460, and you end up with 3143 over 14,460 is 1 over our equivalent. If you inverse that to find the equivalent resistance, that's 14,460 over 3,143 ohms. That's about 4.6 ohms, and that is the equivalent resistance of this network of resistors. So series and parallel circuits add tools that we can use when we're doing circuit analysis to think about what more complicated arrangements of electric circuit elements might do within a circuit. And so this concludes the discussion on series and parallel circuits. Some of the ideas that we've touched on in here, however, will resurface in the Kirchhoff's rules discussion, which is the subject of the next lecture. As always, it's hoped that this was a useful resource for you for learning physics. And if you've noticed any errors in the presentation, I would encourage you to point those out to me. Thanks.